Okay, so 2.3, day 2, continuity. All right, so I do want to have this graph in your notes. Hopefully you did the warm-up in your notes. If not, that's not a big deal. We'll just copy it now. Okay, so 1, 2, 3, 4, 5, 6. 1, 2 on the y-axis. Okay, this is going to be just that graph that you have on the board over there. All right, so here's what a graph looks like. It's closed at 1, at 0, 1, and then it's open at 1, 0. And then it's closed at 1, 1, and it runs over here to 2, 1, but it's open. And there's a point directly above that at 2, 2. And then it goes from 2, 2 to 3, 2. I'm sorry, from 2, 1 to 3, 2. Open on both ends. Drops back down to the point 4, 1. And then it cuts over as a constant function to where x is 5. And it's open. And there's a point at what looks like maybe 5, 1/2. So we really don't need 6 at all. Okay. So we already talked about why it's continuous at 4, and we talked about why it's continuous at 0, one interior point and one end point. So the question now is, where is it not continuous? Okay, so this is the question of where is it discontinuous? All right. Okay, so take a look at it. See if you can jot down the x's where the function is not continuous. Points of discontinuity. Okay, so this could mean a couple things. It could mean that the point doesn't exist. Okay? Those are gimmies. Like, look at 3, x equals 3. There is no f of 3. It doesn't exist. So 3 is definitely a point of discontinuity. Or it could mean that the point exists, but it just isn't filling the hole. Where does that happen on this graph? At x equals 2, right? The limit exists at 2. Limit's fine. It's just f of 2 doesn't agree with the limit as x goes to 2. Or it could just mean that the graph has no limit. That can happen too. So like, look at x equals 1. At x equals 1, there is no limit on both sides. I mean, there's a limit on one side, limit on the other side. They don't agree. So we say that limit doesn't exist. Okay, so let's make a list. So what do we got here? Where are my discontinuities? X is 1, right? Let's write a reason real quick. Because the LIM as x goes to 1 does not exist. We have another discontinuity at x equals 2. It's for a different reason. So what's the reason for that one? F of 2 is what? Yeah, what is f of 2? F of 2 is this point up here, right? So it's f of 2 is 2, but that's not what the limit comes out to, right? What does the limit come out to? The limit near 2, yeah, is 1. If you look at your arrows, they're coming in towards y equals 1. So we have a disagreement with our limit and our function value. Okay, we can say that it is discontinuous at x equals 3 for a third reason. So what's going on at x equals 3? What did we say? there is no f of 3, right? Okay, so you certainly can't say it's continuous. So f of 3 is undefined. We don't write does not exist. We write undefined when a function value is missing. Okay, undefined. And x equals 4 is good, right? We said x equals 4 is continuous. Where's our next discontinuity? X equals 5. The right endpoint is not continuous. Okay. And the reason is, what's the rule for endpoints? The one-sided limit has to match the point, right? What's the one-sided limit at x equals 5? Yeah, the limit on the left of 5 is what? 1. But what is f of 5? Looks like it's only like a half or something. See? So those two are not in agreement. Okay, so I'm just telling you, the AP test is not just about, oh, where is it continuous, where is it not continuous. There's almost always a way they can make you justify it. Okay, so you could know darn well that the graph is not continuous at 3, but they'll list 4 or 5 reasons why. And so you can't just say, oh, it's discontinuous at 3. You have to say exactly why. Does that make sense? You have to justify everything, at least on the free response stuff. And they're good at writing multiple choice questions. I mean, these questions are amazing. They're so well written. They really make you think. So if you've ever taken a look at the test, you'll see what I mean. There's no quick and easy answer. Sometimes, but most of them require some thinking. Okay? So always think of a justification, even if it's not asked. Our book might say, where is it discontinuous? But you need to know exactly why. And maybe you should write it out like I did for practice. Okay, there are some other points where the graph is not continuous. Does anyone know where they are? Yes?
When the x is less than 0 and greater than 5.
You're right. If you're out of domain, right, the graph is discontinuous. Think about it. There is no f of negative 1. There's no f of negative 1.2. So this whole side of the number line is missing. Same thing with everything after 5. So technically those are points of discontinuity also. The graph doesn't continue there. So we're going to write that as well. Because the question didn't say on its domain. It just simply said, where is it discontinuous? Okay. So this is our last bit. It is also discontinuous for all negative numbers and any number greater than 5. Okay, so lots of answers there. Make sure you get those last two. It's just because we're out of domain. Int x. Floor x. Yeah, that function is an interesting one. Okay, let's take a look at that one real quick. So I'm talking about that step function, that staircase-looking one.
Mr. Short,
Let's talk about the discontinuities. Yeah.
how do you get to the int x on the calculator in a faster way than going to catalog?
I think it's under math, numbers. So, this one always makes for a fun discussion when you're talking about continuity. Okay? Because this thing is repetitively discontinuous. Like every time it jumps up a step, you've got to break in the graph. Right? So let's look at this graph together. Why don't you guys go ahead and draw it? If you can draw it from memory. I'll draw it up here too. So it's just a bunch of segments, right? and each one is exactly 1 unit long. There's a closed point on the left and an open point on the right. And this just if I could use staircases as a verb, it's staircases. So it just goes to the next rung of this, or next step on the staircase. And then we've got this one. And this just goes on forever. Okay, and then remember on the left side, that thing just continues. Okay, I do want to warn you about some graphing softwares and some textbooks. So this thing has so many names. In some cases, you'll find in some books and in some like computer softwares or whatever with graphing, if you type int x, I've noticed they'll put this one right here, right here. So all of these steps on the left are raised up a space. So it's not a mistake, it's just a little bit different definition of int x. So the integer function that we're using is the greatest integer less than or equal to the input. For example, you plug in -0.5, which is right here, right? You're supposed to round that down to -1. That's why this error is down here. But in some textbooks, what they do instead is they just sort of truncate off the decimal. And so they'll say, oh, -0.5, that's -0.5, so let's just round it to 0. Just cut off the decimal. So in that case, this step is up higher, and this one is up here, and they're all raised up by space. But in our book and on the AP test, what I've seen, this is the one we use. So it actually looks like a staircase. Every step is 1 inch wide, one unit, not 2. So if you have this here, this will look like it's 2 spaces wide. So just be careful of that. It shouldn't affect you too much unless you're using like WinPlot or some computer software. Okay, let's talk about the points of discontinuity. What are the points of discontinuity? Okay, so this is an interesting question because as far as domain is concerned, the domain is all real numbers, right? There is no x you're not allowed to input. For every single x value, there is a y value. And yet we do have discontinuity because of limits. Okay, so can someone tell me an example of a discontinuity, just looking at the graph? Where is it not continuous? At x equals 1. Okay. Where else? X equals 2. X is equal to 3. Right.
40.
At 0, there's a discontinuity. Right, at -1. In other words, what? X is any integer, right? So where x is any integer, you're going to have a discontinuity. But what's the reason? Is it because there's no such point as f of 1? No, there's an f of 1. Is it because there's no f of 2? No, there's an f of 2. What's the reason? It's those darn limits, right? Anytime you do a limit to the left side of an integer, anytime you're on the left side of an integer, I was going to put f of x, but our function is int. Anytime you're at the left side of an integer, this thing's going to come out to n minus 1. And anytime you're on the right side of an integer, it comes out to n. They're not the same. So the limit at every single integer is a d and e. D and E. So those darn limits don't exist. None of them do. So we can't say that it's continuous. Just an interesting example. Okay. Let's talk about types of discontinuities. Okay, there are many names for discontinuities. I'd like to go back to this picture for a minute. When we're doing this picture, there were many discontinuities. X equals 1, x equals 2, x equals 3, and x equals 5, plus all the stuff that was out of domain, right? All discontinuous for one reason or another. Some of these are not able to be repaired easily. Okay, so let's say someone gave you this thing. I don't know what this is. It's like a blue toy, okay? This is what it's like, some weird blue toy, and they gave it to you, and it's obviously broken. Look at it. It's broken into many pieces. And it used to be one piece, right? How would you fix this toy? Well, if you're at x equals 1, to fix this toy, this disjoint right here, you need to either bring this part of the graph down to fill that hole, or you need to bring this piece up to fill that hole. You've got to get these two pieces to agree. Okay, so you have to like shift this up. See what I mean? Over here, it's not so hard to fix at x equals 2. You just take this point and plop it back where it belongs. Just drop it a space, put it back in the hole. Okay? If you're at x equals 3, looks like that point got lost. Okay? We don't know where it is. It's on the carpet somewhere. Okay? You can tell I have children. That needs to be supplied. Maybe you need to order a new part from the factory, but you can fix it. You can just plop that point right in there once again. Okay? This wasn't broken. X equals 4 is supposed to break. X equals 5, not too hard to fix. You just take this point and plop it back in. Any points that just simply need to be redefined to fill the hole are called removable discontinuities. So I like to think of them as discontinuities that can be easily repaired. This one is easy to repair. I need to move exactly one point. Put it back in its place. This point is easy to repair. I just need to supply a point at x equals 3, and then it'll be filled. X equals 5 is easy to repair. I just need to move this darn 5 comma half to 5 comma 1. Anytime you only need to move one point or supply one point to fill the hole, it's considered removable, easily fixed. The discontinuity is removable. So continuity can be easily restored. Anytime you have to shift an entire piece of the graph to fix it, that's considered not removable. Okay? Not removable. Okay. So let's take a look at some of these types of discontinuities. There are many kinds. First thing you have to know is that this graph is continuous at x equals 0. Okay, so this one isn't even broken. So f is continuous at x equals 0. Okay? Let's look at our second graph. This one has a hole at x equals 0. You would write f is not continuous at x equals 0, but this is a removable discontinuity because it's not hard to fix. You just need to supply one point. You tell me what f of 0 is, and if it's 0, it's going to fill that hole. If f of 0 is 0, right? So just a simple definition would fix it. Okay? Let's look at another one. How about this one? Got a hole there. And it looks like f of 0 is just up a little higher, right? This one is also considered removable. F is not continuous at x equals 0, but it's removable. Why? Because this time all we got to do is supply, not supply a point, excuse me, but move a point. See? Our next one. This one is just kind of hopelessly broken. That thing is, I suppose you could repair it, but it's considered not removable. Because you're going to have to move, even if you drop that red point into the hole, the right half of the graph still won't match up with the left, so the limit's broken and the point's missing, so this is not removable. So f is not continuous at 0. This is not removable. What's another case of one that's not removable? What if you had this? This is a very common thing. If you've got a vertical asymptote, obviously f is not continuous at x equals 0. This is not removable. This is not easy to fix. You got to remove the asymptote, redefine the whole function to get the two pieces to agree. This is what we call an essential discontinuity. It is broken in its very essence. So this is an essential discontinuity, or sometimes called an infinite discontinuity. And it is not removable. And the last one is a really weird one. I'm getting a little low on time because I think we're doing a fire drill today. So I want to make sure I get this one drawn for you. This is a really unusual situation. Okay? You might run into it though. Imagine a function that's oscillatory. So it does like, the sine thing, right? But its period diminishes as you get closer and closer to x equals 0. You guys know what I mean by period?
Yes.
What's going on here? The function is waving, right? But the frequency is increasing as you get near the origin. So it's wiggling tighter and tighter and tighter. Well, this thing's going to have trouble reaching the origin. Okay, it's coming in, but it's slowing down. Every time it crosses the x-axis, it crosses closer to the last point than before. So this thing is it's almost like it's being repelled from the x equals 0 mark. This thing will never reach the origin. So its frequency is increasing. Like you see, its wavelength is decreasing, and it's just like holding back, and it's not going to make it. And this might show up on the right side as well. You've got a nice wide wavelength here, and then it starts getting tighter and tighter and tighter and tighter and tighter and tighter and tighter. Is this thing ever going to reach the origin? No. It can't. What is that thing? You think that's easy to fix?
No.
This thing is called an oscillating discontinuity. F is obviously not continuous at x equals 0, and this oscillating behavior is not only hard to understand, but impossible to fix, really. I don't think you can fix it by putting in one point. I might know that it's x equals 0, but I don't know what the y is. You get my drift. Okay, so there is one other topic in continuity called extensions. But I might have to put that on a separate extension video and post it online. It's not used that often, but I will teach it. I just don't know if I want to use class time for it. Basically, here's the basic idea. You actually kind of did it in pre-calc. A continuous extension would be basically, remember I said that in this second graph, F had a removable discontinuity and that this point needs to be supplied. Well, if you supply that point, that's called the extension. So if you went ahead and told me, okay, Mr. Shore, I'm going to add in one more point, 0, 0, you just provided the extension that fixes this thing. See? So extension is not hard to understand, but I don't want to use class time for it. We can move on to 2-4 tomorrow.